MATLAB has a built-in function called step, which if you give it the numerator and the denominator for your filter, it'll actually give you the step response. And I just thought it might be kind of interesting to see the top filter. Oops, where'd it go? So the top filter is, both of these are step responses for the same filter. So 1 kilohertz pass band, 5 kilohertz stop band, 3 decibels ripple, 60 decibels attenuation. And the top one is the Butterworth filter, and the bottom one is the elliptic filter. And you can see that even though they both achieve more or less the same quality in the frequency domain, in terms of what frequencies they pass and which ones they don't, in response to a step, they give pretty different, pretty different responses. So you could definitely, right away see that if you're concerned about the shape of your waveform, just because it looks good in the frequency domain, you really haven't thought much about what goes on in the time domain. So it's often very easy to forget about it because you look at the frequency and you say, okay, well, the frequencies attenuate or get passed the way I want to, but the time domain is sort of like its own thing, and it's important not to forget about it. Yes. Correct. Correct. And you see the Butterworth filter, very unresponsive in the beginning. You see the Butterworth filter looks like it takes, close to maybe like 1/8 of a millisecond to get going. Right, 125 microseconds to really respond. So it's a slow responding filter. Whereas the other one, sort of right away, it started to have a response. So there's a lot more latency involved in the Butterworth filter. Anyway, I'll put this code online as well. You can download it and play with it. Okay, so change of gears now. We're going to spend the rest of the afternoon discussing the DFT. So question 7 on the list. Who wants to take a hack at this? How is the DFT different than the DTFT? How are they different and how are they similar? Okay, so both of them are giving a frequency response. Chris, how? Okay.
One has a continuous output, and the DTFT has a continuous output, while the DFT has
discrete
output.
Cool. The TFT is periodic. Right, okay, exactly. Mm-hmm. So you're saying the DTFT, it doesn't have to be infinite. It could be infinite if it's periodic. Actually, no, even that's not true. I don't know about that. You could take a DTFT of an infinite signal. Yeah, but you're saying you can't take a DFT of an infinite signal. Did it say that in the book? Okay, I must have just missed it. I think that, okay. That sounds familiar. I must have just skipped over that. Okay, we'll buy that. So there's a fundamental relationship between the DTFT and the DFT. They're intimately linked. Did anybody catch what that relationship is?
I don't know whether I understood it correctly, but I think that the DFT is like sampling of the DTFT.
Absolutely. Yeah, it is. And we're going to see, hopefully we'll have time to buzz through this by the end of the class. It causes some seriously weird things to happen, okay? But predictable, seriously weird things. So let me just draw a quick diagram for you. Hopefully, all right, so we'll start a fresh page. So here's what we've got so far. So DTFT versus DFT. So both of them take discrete, I'm using discrete or digital as synonyms. Discrete or digital is input, but now the DTFT, as we discussed last time, gives you a continuous output, whereas the DFT gives you a discrete output. So last week, we beat on that DTFT till we understood it inside and out. So the beauty of what we're about to do now is that it's essentially the same thing. The DTFT was defined as x of e to the j omega equals sum of x of n e to the minus j omega n summed over all the values of n. So let's say there are capital N samples in X. So that's summed from n equals 0 to n minus 1. Okay, so that gives you a total of n samples. So that was that definition. So now, all I'm saying, so this is a continuous function, right? You could plug any value of omega in here, and you'll get some output. So for the DFT, or at least the DFT in its most vanilla form, we're going to take the DTFT and evaluate it at the following frequencies. Omega equals 2 pi k over n, where k is between 0 and n minus 1. So what does that mean, right? So let's draw a little picture, because pictures make me happy. They make things make more sense. So, all right, let's try hard to draw this. That's almost good enough. So here's our DTFT for some signal. We don't care what. So here's, I know before we drew it between minus pi and pi. Just humor me, for today we're going to draw it between 0 and 2 pi, but it's the same thing. So there's 2 pi, it's close to halfway. There's pi. Do those look symmetric to anyone? No. Watch this. No. Copy. Alright, never mind. Okay, back to the drawing board, obeyed. Okay, pretend those are symmetric. There's your DTFT. So now, let's say I started with a 5-point sequence. Which means now that I want capital X of k to be a 5-point DTFT. Sorry, a 5-point DFT. So that means I'm going to take my 2 pi and divide it into 5. So my frequencies are going to be 2 pi times 0/5, 2 pi times 1/5, 2 pi times 2/5, 3/5, and 4/5. So in other words, what I've drawn on the screen right now is the DTFT evaluated at all the frequencies. The DFT is just that same signal, but sampled in 5 places. So let's see if I can get this right. So that's 1, that's a half, that's 0.5. So half of that is a quarter, so let's see. Here, 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 and here. Let's draw those nice and big. So I started with a 5-point. So x of n had 5 points. I wind up with a 5-point transform of it. And that's it. That's the discrete time Fourier transform. It just tells you how much frequency content is contained in each one of those 5 frequencies. Question so far? No? That's good. So there's actually a formula for this. Very good question. I'm not going to answer it just yet. Give me 10, 15 minutes and we'll answer it. Right, so just so everybody hears the question, though, to think about it. The question is this enough points that we could reconstruct our original signal? So let's hold off on answering that just yet, but there is an answer to that. So the actual definition of the DTFT is as follows. So what I've done is I've just given you the relationship between the DTFT and the DFT. The actual definition of the DFT, which I'm just copying this right out of the book now. So x of k equals the sum from n equals 0 to n minus 1 of x of n times e to the minus j 2 pi k n over n. So that's actually the formal definition from the book. And in words, this is the DTFT sampled at n equally spaced frequencies between 0 and 2 pi rads per sample. Okay? So we just took the DTFT and we sampled it. Questions so far? All right. Okay, let's skip the bit about the orthogonal base just yet. That's important, but we'll skip it for now. So now, the book indicates, I'm on question 9 now. The book indicates that if you have an n-point sequence, its DTFT should have m points, where m is greater than or equal to n. So in the example I just did, my time sequence had n points, and my DFT had n points. They were the same. And that was okay. Now I'm saying, that I've got an n-point time sequence. I'll just write this down so we can all see it. So you have an n-point time sequence. And then m point transformed sequence. The book says that the essential relationship is that m has to be greater than or equal to n. So let's think about Das's question a little bit. The book states that this is sort of like the basic rule. M is greater than n. So before we talk about why that's the case, let's talk about how we actually get that to happen. So let's say that I give you a 3-point sequence. And I ask you to take the 10-point FFT of that. How do I do that? Exactly. So let's say I give you h of n equals 1, 1, 1. So I know now that if I take that formula that we just had on the previous page, so if I take, where did it go? We know if I take this formula, if we just plug and chug, I'm going to get a 3-point DTFT out of that. So in other words, I will have sampled my curve at three equally spaced points. Okay, that's fine. But let's say I'm not interested in that. Let's say I don't want a 3-point DTFT. Let's say I want a 10-point DTFT. How do I do that? The answer I'm hearing is I zero pad. So before I take this h and I stick it in that formula, I'm simply going to pad it with 7 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now I have a 10-point sequence. I take the DTFT of that, and that magic property of my DTFT is that it has the same number of points out as it has going in. So now I'm going to get a 10-point DTFT. Pretty cool, right? Essentially, all that will happen when I've done that is I've taken my okay, good enough. So there's 2 pi, there's pi. So instead of sampling it at, let's see, so if we just did a 3-point DTFT, we'd get a sample at 0, a sample at 1/3, and a sample at 2/3. But now that I've padded it with 7 zeros, I'm actually going to get 10 samples off of that. So it's going to be the same basic DTFT, but now I'm going to sample it just at different places. So now I'm sampling it in 10 different locations. So I'll sample it here, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I missed one. Let's draw it in here, 10. Okay. So it's the same idea. It's essentially, I'm oversampling it. Okay? Does that follow? So, what would happen if I let m be less than n? If m was less than n, would I be able to recreate my original signal? No. Right. That's the magic part of this. So remember now, when you have an analog signal, so let's forget about DTFT for a minute. If you have an analog signal and you sample it, as long as you sample it enough, even though you're missing all the points in between, by theory, you're still able to recreate that signal. So yeah, am I missing some points? Sure. But as long as I've obeyed Nyquist, I should be able to recreate my original signal. The magic of the DTFT is it's exactly the same thing. So if we start with a 3-point sequence, and I create a 3-point DTFT, I should be able to recreate my original signal from that. If I have a 3-point sequence and I take a 10-point DFT, now I've oversampled. I should definitely be able to still reproduce my original signal. But what if I do a 2-point DFT? Should I be able to get my original signal back? No, because you've undersampled. Essentially, you've failed to satisfy the Nyquist criteria. But instead of sampling a time signal, now we're sampling a frequency signal. But we still have to obey Nyquist. And sort of the way that winds up panning out is that this is required to satisfy Nyquist. All right. Let me show you some examples in MATLAB. Are there questions so far? This stuff's kind of cranky. I think it's easiest just to do with real, with actual examples. So clear, close. Yeah. Yep. Let's just try it and see if it works. I'll answer that in a minute. It's counterintuitive. Essentially, what you're banking on is that as long as you sample enough, no information is being lost. Let me run through the example. Hopefully it'll make a little bit more sense. So let's start with, what did I call that? FH or H. Okay. So here's a very simple time sequence. So a quarter, a quarter, a quarter, a quarter. And it's of length 4. So there are certain MATLAB hotkeys that are apparently also hotkeys for the recording software, and they're fighting with each other. Okay, so I want to evaluate the highlighted code. Okay, let's do like this. Cell, evaluate current cell. So who's stem n orig h orig. So here's my original sequence. It's just 4 points, each one of value a quarter. Everyone happy? So now I'm going to take the DFT. Now I can do that in one of two ways. If I wish, I can just use the MATLAB command called FFT. So FFT stands for Fast Fourier Transform, and it's just a mathematical algorithm for computing the DFT. So FFT implements DFT. That's why they're labeled differently. But so if I wanted to, I could just say H equals FFT. Let's call it H. Just so I can differentiate it from the other H. H sub FFT of H orig. Oops. Equals FFT. All right, so there's my FFT. It actually turns out that my FFT is just 1, 0, 0, 0. Let's not pay too much attention to what the values are. We don't really know how to interpret those anyway. So let's not fret about what the actual values are. Okay. So one option is I could have just taken the FFT. Alternatively, for reasons that I've just explained, I could use freq-z, taking care to ensure that I evaluate it not just at any frequencies, but at the frequencies that are, remember it was 2 pi times 0 over m, 1 over m, 2 over m, 3 over m, however many times I'm going to sample the DTFT. So in this case, we started with 4, and I actually want to do a 4-point FFT, or a 4-point DFT of my signal. So I'm just going to evaluate freq z at with m equal 4. We'll follow what I did? Yeah. I'm sorry. I'm trying to make the code bigger. No, it's let me just take a second. I think I can actually increase the font size. Display. Where am I? Fonts. You can't see 10? This is terrible. Okay, that might be a bit much. Is that better? Oh, hey, how about that? All right, every week we'll improve on something until we have to end the semester, right? Okay, so you recall that before we were talking about, we're going to take the DTFT, and we're going to sample it at, so in this example we were doing 5. We were sampling it in 5 locations, so we did 0, 1, 2, 3, and 4, so that's a total of 5 options. So, I don't follow you. No, I don't think that's the case. I think, let me chew on that for a minute. The intuitive backing from where Nyquist comes from when you're sampling the frequency domain is a little bit slippery. Let me just think about it so I can phrase it properly before I give you a wrong answer. Okay, for now I'm just taking freq z and I'm evaluating it at those same frequencies that we talk about. So 2 pi and then 0, 1, 2, and 3. So at this point, I'm just going to evaluate the DTFT, sorry, the DFT. And let's see. So my H, it's actually exactly what I had before. So before, when I did it using the FFT, I got 1, 0, 0, 0. And when I do it the other method using the freq z, I get the same thing. It's 1, 0, 0, 0. There's some rounding error. That's why you have 0 plus 0i, but it's basically 0. So the first lesson is, as far as MATLAB is concerned, it doesn't matter if you use FFT or if you use freq z. As long as you evaluate freq z at the correct frequencies, they should provide the same. They should provide the same Fourier transform. Okay. I mean, clearly it doesn't follow exactly the same function because there is some sort of rounding error there, but I think it's more or less the same thing. freq z uses FFT. I suspect where they may differ slightly is how they pad for zeros. Because I think FFT always has to work with powers of 2. Right. I don't know yeah, at some point they're both relying on the FFT algorithm, but what they do before they apply the FFT, I don't know. They may pad with different numbers of zeros and then downsample. Yeah. Yeah, they both should give the same. Yeah, absolutely. I mean, we could just have easily have said, give me a 7-point FFT, right? We could do that. So if I do that, so let me just clear this. So MATLAB has computed that for the DFT, and so the only problem now is I have to pad this with 3 zeros. Right, because HRIG has 4, so now I pad it with 3 samples, and those are exactly the same. So it doesn't matter how many samples you do, as long as you evaluate freq Z at the correct frequencies, FFT and freq Z should give you the same thing. Okay? All right, so let me back up for a minute. Let me go back to, just to keep life simple, let me go back to 4. And the reason I picked 4 is that my original signal has 4, my FFT has 4. You know, we should be on the same page. So as far as here, this evaluates the FFT, or the DFT. And now down here, I'm just going to reconstruct it. So remember last week, in the homework, I asked you to do this without using a for loop. But just to make life easy, I've put it in the for loop. This is just the code that we looked at before to reconstruct your signal from the FFT. So it's just the backwards DTFT. So in principle, if I had sampled my DTFT with enough points, then when I take the inverse DFT, I should get my original signal back. So let's try that. So the top line is the original, and the bottom one is I've taken the DFT from the first point, so I had 4 points in, I had a 4-point DFT, then I took the inverse transform of that 4-point DFT, and I got exactly my signal back. So it works, right? So even though I only sampled that DTFT in 4 places, that was sampling it sufficiently high enough to get all the information. So there's no information lost there. Because if I lost information, I wouldn't have recreated my signal. Right, and this is, you can sort of convince yourself that this isn't just an arbitrary, maybe I just got lucky, right, with this sequence. What if I tried, some other sequence, right? So let's do, 1 through 7. Oops, let me get rid of that. So it works. So in this case, I have a time sequence with 7 points in it, so 0, 1 through 6. So I sampled, that means when I took its DFT, that means I sampled the DTFT in 7 places, and that happened to be just barely enough samples that I had captured all the information out of that DTFT, and I know that it was enough to capture all that information, because when I take its inverse, I successfully gain back the original signal. It's pretty cool, right? So now you can take that DTFT, and as long as you sample it at the Nyquist, right, whatever Nyquist is, you can get your original signal back, even though you threw away all that other information about what was going on at all those other frequencies. Anyone confused yet? Gets worse, but much cooler. Okay, let's take the next step. Well, let's sample higher. Let me go back to, so let's go back to our humble a quarter, a quarter, a quarter, a quarter. So now let's sample it, let's oversample it. So we're pretty sure if we oversample it, we should get the original signal back. So now I'm going to sample the DTFT 10 times. I know I only need to sample it 4, but now I'm going to sample it 10 times. Okay, no one's surprised, we got our signal back. All right, so now let's try undersampling it. So we know the minimum now to satisfy Nyquist is we need to sample this DTFT 4 times. So I'm going to sample it 3 times. Chaos, right? So instead of getting a quarter, a quarter, a quarter, a quarter, now I can't get my original signal back. I'm sorry? We're actually going to figure out where this comes from, and you're onto something there. Let's try something we haven't tried yet. Let me put this back at 10. Now, when I compute my inverse DTFT, let me just get rid of this. This is in the way. All right, I'm going right off the equation sheet. When I compute my inverse DTFT, essentially I'm just performing the following computation. Sorry, it's k equals 0 to m minus 1. X of k e to the negative j 2 pi k n over, I believe it's m. So that's the formula. Now tell me something. So when I'm computing my inverse Fourier transform, so let's say that I started with 4 points. So I'm taking the inverse DTFT, or DFT, I'm taking a 4-point inverse transform. So in other words, I know I'm expecting 4 points back. So in other words, I let n equal 0, 1, 2, and 3. Is there any reason why I can't evaluate that at other values of n? I mean, what if I wanted to evaluate it at n equals 4, 5, 6, 7, 8? Can I do that? Why not? I mean, will I not be able to evaluate it? Yeah, it'll evaluate. Let's just try it, see what happens. This is where it really gets kind of makes your head spin a little bit. So all I'm going to do is I'm going to say, let's take that inverse transform, but instead of only looking at, let's say, 4 points, let's look at the first 20 points. Okay, so here's the first 20 points. So let's recap. I've got a 4-point DTFT, sorry, a 4-point time signal. I'm sampling its DTFT in 10 places, and now I'm taking its inverse transform, but instead of only looking at the first 4 points, I'm going to look at, let's actually make it a little more. Let's make it 30 points. It's repeating. So let's see what happened here. We took this, we sampled its DTFT in 10 places. When I take the inverse DTFT, we can see that I get the correct signal, but it's repeating with what frequency? 10. Right? So 0, 10, 20. It's periodic.
Okay, if you taking in equal to 4, then it will be 4.
Exactly, right? So now we can start to see what happens if I decrease m. So this is m equals 10. What if I let m equal 5? Right? So 4-point sequence. So I still get my original signal back. So now what's the smallest value of m I can have? 4. What happens when I have m equal 3? Right, it's going to alias. But here's the cool thing. You can predict how it's going to alias. So So now this is when they're separated by 5. Then if there were 4, they'd be here. Then if they were separated by 3, then this one would be sitting on top of this one. So what would you expect? You'd expect to have a quarter, two quarters added together, so 0.5. So a quarter, 0.5, a quarter, 0.5, so on and so forth. Well, if we try that, a quarter, 0.5, a quarter, 0.5. Yes?
Why is the first one like that?
It's circular convolution, which we're actually going to talk about next time. So I'll do a little hand waving and convince you that if you think about it, I could have plugged in -1 for n, right? Why did I have to start at n equals 0, right? I could have started at, if you think about it, this extends not only infinitely in this direction, but infinitely in this direction as well. So at some point, they're just going to all start overlapping. And so I guess that's why that one equals 1/2. That's a good question. So that's where Nyquist comes to play in this problem, is that as you decrease your sampling period, these guys start to overlap some more. Now, this shouldn't be surprising, because in traditional sampling theory, we know that if you've got a time signal, so let's say this is the signal in time, and now you transfer it to the frequency domain. So this is in analog now. So let's say this is the sampling frequency in analog. So analog signal, analog Fourier transform. So actually what I mean to take, what I shouldn't have drawn here, let me start over. I didn't mean to draw the actual samples. So we know that when I actually sample it, then what happens in the time domain, it becomes periodic, right? And it becomes periodic according to your sampling period. All right. Now, if your sampling period is more than double your bandwidth, you're guaranteed that there won't be any overlap here, right? That's where Nyquist comes from. As you decrease your sampling rate, you're okay until these things start to overlap, and then you have aliasing. Well, it's exactly the same thing now, except instead of sampling in the time domain, we're sampling the frequency domain. So in other words, you had a signal that's continuous in frequency, which, let's try it like this. So now for the DFT, we started with a signal that was continuous in frequency. Which means that in the time domain, it had some sort of, some number of samples, let's say. Then when we sample the frequency-based signal, we're going to do the same thing. This signal, the time-based signal, becomes repeated. And the repeat frequency, right, the period just happens to be the frequency, the number of samples you take of that DTFT in the first place. So there's this there's this symmetry here, right? It shouldn't surprise us that we have this repeating process. So every time you sample, you wind up with the same signal getting repeated over and over again. As you decrease the number of samples, that's when things start to overlap, and eventually you get aliasing. But aliasing in a very predictable manner, right? You see how we were able to predict those samples? So if we come back here and I change, so let's say I go back to 7 points, and I take a 6-point DFT. What's the first point I should get? What will h of 0 be when I reconstruct it? No, I'm not dealing with this anymore. Now this is my signal, 1 through 7. Almost. It's actually, the signal starts at 1 and ends at 7. It'll be 8. It'll be 1 plus 7. Right, so it'll be 8, 2, 3, 4, 5, 6, 8. Right, so let's try that. There it is. 8, 2, 3, 4, 5, 6, 8, 2, 3, 4, 5, 6, 8. So they're alias. That's pretty cool. I mean, to me, it's fascinating that you could take a digital signal with a continuous frequency domain, sample that frequency domain, and then throw away the rest of that information, but you know you've got enough information to reconstruct the original signal. I guess the intuition behind that is that if you satisfied Nyquist in the first place when you sampled your signal, then you've placed certain restrictions on the DTFT. So that when you sample it, you know that you only need, if you had n points in the first place, you should only need n points of the DTFT. What do people think of that? Is that too much hand waving, or? That's the point. You don't. You've aliased. Once you alias, you're hosed. You've lost it. It's actually worse than losing it. You've actually polluted it. So you don't know whether this signal originated from 1, 2, 3, 4, 5, 6, 7 that was alias. It could have originated from 2, 3, 4, 5, 6, 8. Right? You just don't know. So you've introduced this level of ambiguity in there now that there's no reason why any one of an infinite number of solutions, of sources, aliased in different ways couldn't have achieved the red. Absolutely. Right, exactly. It's worse than just dropping. You've actually introduced lousy data. Yes? Ooh, okay, that's a good question. Yes. I think you can use, let's try this. There's IFFT. I'm just wondering if it'll do exactly the same thing as this. R reconstruct equals IFFT of H. All right, bad things usually happen to me when I go off the menu. See? Well, let's see if we can figure this out real quick. Oh, it didn't like that, did it? Close, stem, page, reconstruct. So you're saying, let's see, I put this up at 7. Still didn't like it. Post MR H reconstruct. Yeah, there's you would think that you would just be able to plug it into the eye. Let me just read this real quick. Maybe I need to use a symmetric. Let me just try that real quick. Solve any problems? No. Yeah, there you go. It did work. I just had to tell it. Okay, a subtle difference in the way the IFFT is computed. I think, not that you care, but since you asked the question, I'll answer it. When the IFFT does its computation, I think it's expecting its points to go from minus pi to pi. But in this sample, our frequencies were going from 0 to 2 pi. And I think that symmetric flag let it pick up on that. I'm pretty sure is what just happened. With IFFT? Yeah, I'll take that. You know, it's if it works, right? I mean, it's. I'll accept that. That'll work. That should work fine. The only question in my mind is why is H reconstruct not plotting properly? In any event, that's not too crucial. N is 30 points. Oh, right, because can I tell it how many points I want for IFFT as well? I can specify. Okay, so now I can say give me the length of N yeah? Alright, well, clearly there's some issues to work out, but in principle it works. I just have to get the right combination of N and symmetric, but yeah, it should work. I'll figure that out. I'll make sure I'll put the right version of that in the before I post it tomorrow night or tomorrow. Well, we're almost out of time. Let me just look at the list. So, are there any questions about what we've shown so far? It's a little bit dizzying. I hope I haven't. It was not my goal to overwhelm anybody, but there are these sort of elegant symmetries to the sampling theory. You know, sampling in time versus sampling in frequency, but you know, it's the same principle kind of applies both ways, and I think there's a certain elegance to that. I guess we've sort of answered question 12, right? Suppose you're given an m-point DTFT and told that it represents an m-point time-based sequence. How could you work backwards? The answer is it doesn't make a difference. You just follow whatever the rules are that we use for following an inverse DTFT. You just work backwards, and the math just makes it so that all those other points work out. The zero padded points will pad backwards to 0. You'll get those 0 padded points back, which is very cool. Doesn't seem like it should work, but it does. I think that's pretty much it. I don't really have anything else I want to sort of cover, unless there are, just open the floor to general questions. We can finish a little bit early tonight, like 5 minutes.
Can you do question number 8 for the orthogonal range?
Yeah, actually, that's a good idea. We can do that. I actually had a hard time putting this into words. Maybe one of you is more eloquent than I am. Somebody have a good explanation of a good English language explanation of what an orthogonal base is? I can take a hack at it. but I suspect someone is more eloquent than I. Let's have it. I'll take that. Right. So inner product of any two elements is 0. So in other words, when you have, so we often talk about a basis, right? And a basis is a set of vectors that you can combine together to form other vectors. And an orthogonal basis, so for example, let's say that I'm talking about the xy plane, right? So nothing fancy, x and y. So I could say that, so these two vectors constitute a basis. So in other words, I can create any other point as a linear combination of these two, right? So if I call this A and this B, then I can say that point X equals, what is it, 2 times A plus 3 times B. That means it's a basis, right? I can get all the points on this plane as a linear combination of those two things. What makes it orthogonal is that I can't get B from A and vice versa. So I can sort of express it two ways. I can say that the inner product is 0, or I can say that, so the inner product would be, the inner product is like saying this times this plus this times this equals 0. If you project one onto the other, you get 0. What that means in words is that there's no combination, so there's no way to get B from A. Like you can't multiply A by 7 and subtract 3 times B to get B. Like it's just not going to happen. Now, there could be other orthogonal bases, right? So for this same coordinate system, you could have 1, 1, and 1, negative 1. Right? That's also an orthogonal basis. And if you were to draw them, sort of the key thing in both cases, yep, absolutely. Yep, because they're perpendicular to each other. Well, it depends. Right now, I've just drawn a two-dimensional space, right? We could have a three-dimensional or four-dimensional or n-dimensional space. So in any event, they're a basis because you can add them together to get all the other points. They're orthogonal in that they're perpendicular to each other. Now, the reason why that's applicable to the DFT is that okay, they go through a little bit of song and dance on the math, but essentially what they're arguing is that when you take the DTFT, you've got the sum over n of x of n, and they introduce this w sub n of k to the n, where wn is e to the minus j 2 pi over n. So let me just clean this up a bit. So this is raised to the, so essentially I've just rewritten the definition of the DFT, but I've insisted on specifically defining this wn term. And essentially all you're saying is that the signal x of k is a linear sum of all your bases, right? So in this case, let's say n is 3. Your basis, you have an orthogonal basis that's e to the minus j, sorry, it's actually e to the you have an orthogonal basis that's e to the 0, 0, e to the minus j 2 pi over n, and 0, 0, e to the minus j 2 pi, I'm sorry, this is not n. I can actually plug in the value of 3 here. And this is 2/3. Thank you, 3. So in other words, A, B, C. X of k can be represented as a linear sum, always, of some number times, I'm running out of variables, some number times A plus some number times B plus some number times C, where A, B, and C are complex. No. I'm sorry, let me just back up for a second. I got ahead of myself. Those are going to be x of 0, x of 1, and x of 2. So it's just like before, I was saying that when you have an orthogonal basis, you can create all the other points in your space as a linear sum of your basis elements. And it's the same thing here. My DTFT can be represented always as a linear sum of my basis. What's my basis? My basis is these points. Who cares, right? So what? Basically, it just works out that when you have a transform that's built off of an orthogonal basis, it winds up picking up all these cool properties that it wouldn't have had if you didn't use an orthogonal basis.
Small x n, say this is w, this is w, then we get the inverse as just complementing that word, getting Hamilton matrix of w.
I'm not sure I follow you.
Complex one is you just multiply with the complex one here, you will get the inverse. If it is orthogonal, the basis is orthogonal.
I'll get the inverse of the
Inverse IDFT. I'm talking about DFT. Which is exponential basis.
okay.
So if we just change the complex conjugate of it and multiply with the DFT function, we will get the.
We'll get back. Yes, absolutely.
That is the property.
There are others, but yeah. The most important is called Parsifal's theorem. It's in the book. Just take a look at it if you didn't get a chance. I don't want to write it because I don't want anyone to miss the shuttle. The guy just called for shuttle. So if you need to go get the shuttle, please run. Otherwise, I will send out the homework questions. The reading questions for next week will go up tomorrow. That's all I have. So thank you.